In this session, let's understand CAP theorem. This is very important theorem in microservices architecture, in microservices development. What this theorem says is that there are three aspects to consider in a microservices architecture: consistency, availability, and partition tolerance. What this theorem says is that you cannot have all the three, you can have only two of them, any two of them. So let's understand what these are in detail. So CAP theorem is also known as the Brewer's theorem, is a fundamental principle in distributed systems. So what are distributed systems? Distributed systems are like, I have one application, I have another application, I have another application. These are all distributed in different environments, right? So these are all different microservices, maybe in different networks, maybe different services, maybe in different environments, maybe in different regions, right? So this is all distributed system. In such a distributed system, particularly relevant to microservices, it states that in a distributed system, it is impossible to simultaneously guarantee all three of the following. So what is consistency? So what consistency means is that if you know relational database like Oracle or MySQL, you know ACID properties, right? That means any transaction you do, it is guaranteed that when you request a response from it or when you read the update, you will get a latest value, right? You won't get two different answers. So what consistency says is that every read receives the most recent write or an error. So what it means, this is the database. I have one table, and then in this table I do one operation to insert a value. Okay, now when I read it, so first step is inserting a value, then second step is to reading a value, right? Then I get the latest value that is inserted, or if I do an update, then I get the latest value that is updated. It is guaranteed. That is called consistency. Now if you want consistency, then there is a process that this system does, that it won't allow when it will only send you the latest update. So for that it follows one mechanism. Now this is what it means: every read receives the most recent write. Availability means that every request, read or write, receives a response. That means if I send an update, if I ask a database to give me a response, it will give a response guaranteed. Okay, even though if it is not most recent, but you will get a response. That means the system is live. Suppose if this microservices is calling this microservices, it will receive a response. It may be not the latest value, but it will definitely get a response. That is called availability. Otherwise the service is not available, right? So if you're saying the service is available, that means it will respond to a request. Now partition tolerance means the system continues to operate despite partitioning due to network failures. Suppose there is a failure in the network, the communication didn't happen between these two, but still there will be, the whole system will be working. That is called partition tolerance. Now to summarize, consistency says that you get the same answer each time you ask the question. You don't get different answers. Availability means you will get definitely one answer. That means system is available. And partition tolerance means when there is a network failure between the two communication, like requester and then responder, or one microservices who is requesting and the other microservices who is responding, if there is any network failure, still the whole system works. Now let me say that since the theorem says that you can take only two of them, that means you compromise on partition, or you compromise on consistency, or if you do this, you compromise on availability. So only two of them are possible, and the other one you have to compromise. That is what the theorem says. Let's get into detail, and I will explain you with some example. So for easier understanding, let's take, we have an e-commerce system, and then in an e-commerce system, let's see how CAP theorem works. I create one service, order service. So let me call this as an order service. What it does, users will send orders to it, like I want to buy this product, and this system is responsible to handle the user orders. Now I have one more system, which is an inventory service, which maintains, like say this product I have 10 in stock, one order came, now running balance is 9, one is sold. Now another order came, then it has 8. So for each of different products, it will maintain a running total of how many running value of how many stock is available. This is inventory service, manage products and stock levels. And we'll create one more service which will a notification service, like an order came, inventory is detected, and and customer receives a notification that your order is placed. Send notifications to customers about their orders. So let's assume this is the notification service, and we use these three services in a application, in our example applications. In a real world application, there will be many microservices that handle this entire scenario, but for simplicity, let us take, there are three services: order service, inventory service, and notification service. Let me explain CAP theorem with these three. So as I mentioned, there are different scenarios. Let's take the first scenario, where consistency plus partition tolerance. That means we are sacrificing availability. C, A, P, we are taking a CP, and availability is compromised. So how it happens? Now, strong consistency is ensured across microservices, because we are saying prioritized is consistency. That means strong consistency is required. That means data should be same. The value should be same. Whenever we request a updated value, we should always get the same updated value. Consistent answer should come. Like if I ask how many count of products are there, sometimes it should tell 10, sometimes it should tell 9, means we don't have consistency. We need to have consistent response, right? Even during network partitions, even if the failure happens between the requester and the service provider application, still the consistency should be maintained. So let's take this. User places an order. The order service checks the inventory service. That means it sends a request to inventory service to check the availability. A network partition occurs. That means, say for example, now it failed. The order service retries the request until it gets a response or timeout. It sends again, it retries, or it will finally request timeout. The system ensures consistency, but the user may experience delays or errors. So what happens? Since we want to give a consistent response, even when there is a failure, we don't send a response at all, because we cannot communicate with it. That doesn't mean that we will tell some answer to the customer. We will not tell any answer. We will say an error, or we will experience, the user will get a delayed response. That means here the order service may get a response or may get an error, but may not get a inconsistent value, right? So this is what is the example. Now what do we do in such scenarios? In such scenarios, what we do is a synchronous communication handle. Let me give these three topics: synchronous communication, transaction management, and partition tolerance. This communication is two types: asynchronous communication and synchronous communication. So in synchronous communication, a service requests B and waits for a response from B and receives a response. This is synchronous. Whereas asynchronous communication is A sends a request to B, and then A proceeds. Sometime later, B sends a response, and then A reviews the response and takes the action further. So this is asynchronous communication, right? So in such cases where we want high consistency, we want to wait for the response from B. That's why we use a synchronous communication. The order service synchronously communicates with the inventory service to check stock before confirming an order. The stock is only reduced if the order is successfully processed. That means payment is also done. Otherwise, it will be rolling back, like in a transaction. A transaction is a set of activities, like reduce, add one offer order, and then reduce the count of the stock, then verify the payment, and then verify if the payment is credited to the account, and then you make the process, like you send a notification to the user that the order is successfully placed. All this one is one transaction. For example, if the user payment fails, then all this will be rolled back. The count 10 in inventory becomes 9, and again it will be rolled back to 10, right? So before confirming an order, the order is successfully processed. If the inventory service is unreachable, the order service retries or fails gracefully with an error. That's why we are saying high consistency. That means our order service will get an error if there is a partition problem, if there is a network problem. If order service cannot communicate with inventory service, it won't just tell some answer and then proceeds. It will say an error. It will fail. Then again, transaction management, as I explained, the transaction management, all the steps should be done, otherwise it will be rolled back. So this is called two-phase commit. I'll explain in detail what two-phase commit is in a separate video. This ensures consistency across microservices. This guarantees that changes to the database in both the services occur atomically or not at all. That means either all the services are updated or none of them are updated. Order service, notification service, and inventory service. So orders have to say the status is done. Inventory has to say the count is reduced by 1. Notification have to send a notification that order is successfully placed. All of them will be rolled back or none of them will be executed in a transaction. And then partition tolerance system relies on timeouts and retries. As you see, this service, order service, is dependent on the response from inventory service. So if inventory service is not responding, what it will do? It will do a retry. Again, it will, if it not get, it will retry for 3 times and it will wait for some time. And if it don't get a response, again it will retry. That wait period is the timeout period. To handle network partitions, the services might use a quorum based approach. Like, it's not like one service, there are multiple services, multiple copies of the service, and then we use a quorum technique where writing for a majority of the nodes to confirm the state to ensure consistency before proceeding. I will explain quorum based approach in a separate video. Now what happens, microservices with the Kubernetes, and the whole logic of microservices is that we will be able to scale an application to millions of requests, right? How it is possible? By scaling. Now what to scale in this case? So here auto scaling for such services typically occurs at the API gateway level. Can you tell me why it happens at API gateway level? Because at API gateway level, if these are the 3 services and we get an API gate, this is an API gateway from external, user is calling the API gateway, which in turn calls these services, right? So if something is failing here, if it is not working, we should not accept more requests, right? Otherwise the system gets blocked, right? So what we do, we limit the number of requests that the system can take in such cases, right? So we do a load balancing and then we handle the spikes in the request volumes, ensuring the retries and blocked threads do not overwhelm the system. So what we should remember is, in a system where we are prioritizing consistency and partition tolerance, the API gateway scaling need to be understood, and how it should be scaled we should think in our design. Okay, we should limit the number of requests we get into the system. Let's see the second example where we have availability and partition tolerance. So we are sacrificing consistency. So what it means is that in AP systems, requests are always processed because availability we are prioritizing. Even during partitions, even if there is a network failure, still availability is ensured, but the data may become inconsistent temporarily. So this is important. So inconsistent temporarily, but after some time, eventually they become consistent. So the difference between temporarily and eventually is a few seconds only. Ensures that all microservices synchronize their data later. So we have 3 microservices: order, inventory, and then notification service, right? Suppose when order is asking the inventory and there is a network failure happens, this will not wait for a response from here, and then it will proceed. So let's see in detail. So the user places an order, the first step, the order service immediately confirms the order without checking the inventory service. If the product is out of stock, the system resolves the inconsistency later by cancelling the order and notifying the user. So as soon as an order is placed, it will give a response. It won't wait for the inventory service to update and then respond back if the item is available or not. It will only say that okay, order is placed, and then a order successfully placed notification is sent. Then later, asynchronously, if it identifies that okay, I don't have the stock in the database, it is already 0, I can't proceed with the order, then it sends another notification, sorry, your order is cancelled, we could not serve you with this request because we are out of stock. So this way the product is out of stock and system resolves the inconsistency later by cancelling the order and notifying the user. So in this case, how to do it technically? So let us see. So eventual consistency, that means the order service and inventory service communicate asynchronously using queues, and updates are propagated to other services after a delay, ensuring eventual consistency. Now you need to know what a queue is. A queue is like this. Suppose this is a consumer, like here the inventory service, and this is a order service which is a producer. So it gives like okay, this is the order number, this is the order number, this is the order number. So it keeps sending these orders into a queue and it pushes here into the queue and then sends a response to the user. It won't wait what happened, whether this is processed or not. So it works on its own by just pushing each order into a queue, and this one, suppose if it is down, it will not process the queue. Once it comes up, it will process the queue. And also if there are multiple replicas of this inventory service, the first one goes here, second one goes here, third one goes here. Suppose third one fails, then once the first one is done, then it goes here, then it goes here. So it automatically processes these objects, I mean orders that come into the queue asynchronously. Okay. Now Kafka handles on a topic based. We'll discuss about Kafka and its advantages in a how it can handle large number of services messages. Now let's see fallback mechanism. So this is another technique what it uses. If the inventory service is unavailable, the order services temporarily assumes the product is in stock, allowing the order to be processed. The service reconciles the discrepancies once the partition is resolved. That means once the network is again established. So here is the assumption that the stock is always available, right? Based on that, we will proceed. We will make the decision that okay, order should be confirmed as soon as we get an order. Later, we will reconcile whether we have the stock or not and then notify the user. So this is a business decision on which service should be always available, which should maintain consistency, and we should handle partition tolerance. Now let's see the third one, partition tolerance. Microservices use circuit breakers, like I explained in some other video. Circuit breakers prevent the cascading of the failure of different microservices. Assume I have these microservices. Suppose it is not responding. If this microservices is not responding and not giving a response here, that doesn't mean this should stop, and the whole network should stop, right? It will break it and then it will reassume later on. So the circuit breakers prevent the cascading of the failures, or the dependent services will not fail and we break the circuit. And then queues prevent the failures from cascading. Queues, as I mentioned here, provide asynchronous communication. For instance, if the inventory service is down, the order service routes request to a backup service or logs them for later processing, or put the orders in a queue. Okay, so now as you see here, what we are handling, eventual consistency. We are handling eventual consistency by introducing a queue, fallback mechanism by reconciling the data and then providing a later responses. After the partition is resolved, it will verify what happened, and then partition tolerance by using queues and circuit breakers. Now here you can see what auto scaling should be done. AP systems focuses on maintaining service availability. That means this always the service should be available. Order service should always be available. So if a message queue loads spikes, the system scales the queue consumers to process updates faster. As I mentioned, suppose a lot of queue objects are there, so many objects are there, then the copies of inventory service are automatically created. So if 5 copies are there and if it is not able to handle and more orders are coming, the 5 automatically becomes maybe 6, maybe 10. And then once it reaches some more number of microservices, the queue is resolved faster, right? So auto scaling happens to ensure availability. Here, to ensure availability of invoice service, auto scaling happens and copies of the service are automatically created by the Kubernetes environment. Okay, now let's see the third scenario where consistency and availability are prioritized. Here consistency and availability are prioritized, but partition tolerance is sacrificed. That means if there is a failure, it's a failure. Now let's see how it is done. It is called rare because if partition tolerance is sacrificed, then what is the purpose of building a highly scalable microservices architecture? I need a microservices architecture so that I can handle a lot of requests. I can scale the application, right? So I need to handle the network failures. That's the reason why we created different microservices to maintain their own life cycle and then to deploy and then test and then enhance each of them independently and to copy to create their own replica sets to handle whatever requirement we have to scale and consume the resources. That's the purpose of having the microservices architecture. If it can't handle the partition tolerance, then the purpose of microservices is not properly served. That's why this is called a rare combination. The system ensures real-time consistency and availability, but it fails during a partition since it cannot tolerate network splits. Like let's take the same example. User places an order. The order service verifies stock availability with the inventory service using a shared database. So here is the technique. If a network partition occurs, the system becomes temporarily unavailable, ensuring no inconsistent state is created. That means this is an order service, this is an inventory service, right? Now if I have a if I use the same database, that means order service also refers to the database, inventory service also refers to the same database. And you may ask why? Because this is just for ordering purpose, right? For users interface. Whereas this can be for inventory manager or some other person who is a stock manager who reads these reports and then they may utilize it for their reporting purpose or for further ordering with their vendors. So these two services use the same data. So if I is not available, still O will be able to get the data. So if a network partition occurs, the system becomes temporarily unavailable, ensuring no inconsistent state is created. So there is no inconsistent state because they share the same database. Okay, so this is a design decision we have to make how we want to handle what scenario. Now you can see how it is handled. So a single region deployment. So we should not put because these two are connected to one database, maybe we should put all of them in one region to avoid partitions. That means network failures, services are tightly coupled and often deployed within the same region or the data center. Communication between the order service and inventory service happens in real time using shared database. Now database replication. Database are strongly consistent replication. This is called leader based replication. We'll explain later in some other video. To ensure all nodes have up-to-date data before responding to request. Say what it means is this is one database, right? Suppose I created copies of this database. Now I have ordered one order and then I have to add one count to the number of orders. Suppose I have a number of orders 5. When a new order comes, it becomes 6. It becomes 6 in one of the database and it should wait till all the replica of this 6 appears in all the other databases. That means the records in all the databases copies are updated. till the time whenever someone requests what is the count of the orders, it will wait, it will not respond, it will wait, and once the replication is done, it will say this is the value 6, latest one. So to how it does it, each one says yes I am updated, yes I am updated, yes I am updated, and once all the updates are received and a notification that all of them are updated, then only a next request is handled. This is called up-to-date data before responding, leader-based replication. Okay, this sacrifices partition tolerance. Now, how it handles in partition? If a partition does occur, in fact, we can't prevent. If the partition does occur, the system stops processing the request. To prevent inconsistencies, display an error to the user. It seems like a monolithic application, right? So I have one database, we have multiple services, and if the network fails, then throw an error that we could not reach it, or some database is down, or some other, network failure error like server is busy, some other, errors like 404, different type of errors it will throw. So it is same like a microservice, monolithic application. Now let's see auto scaling. So CA systems rarely auto scale. That means very difficult to auto scale across regions because they prioritize consistency. Instead, they scale vertically within a single region to maintain low latency and consistency. What is vertical scaling? That means I have one application. It is deployed on a OS, which is deployed on a hardware, right? Hardware has memory and CPU. Okay, now it is handling say 1000 requests. I want to scale it to say 1 lakh request, 100k requests. So since this is one application, to scale it, I have to increase the memory, I have to increase the CPU. Instead of 5 GB, maybe I will have to upgrade to 10 GB of memory, and a CPU, I may have to increase the CPU also to as much scale as required. This is called vertical scaling. That means we increase the hardware, vertical scale, but there is a limit, like how much memory I can increase, how much CPU I can increase. It is limited by the hardware technology available, right? Now there is a question like which one to choose when. This is the architectural decision we make based on the business requirements. For an e-commerce application, as we are going through this example, CP is suitable for critical services like payment processing and inventory locking. So we need to prioritize consistency and partition tolerance. Now availability and partition works best for user facing services like product catalog. That means I have a catalog of say 10 products. Suppose I add a new product, a 11th product. User may not see 11th one is also fine, but we will show 10. Maybe after some time user see the 11th one. It's okay, but user should see some response. It should not throw some error, right? So in a catalog service or a notification service, we can make availability as a priority and partition tolerance as a priority, compromising consistency. Now another example is where consistency and availability is rarely used in distributed systems, but may apply to small scale high consistency applications. So if you are building a small application with high consistency requirement, then you go for a monolithic kind of application where partition tolerance is compromised. By employing techniques like eventual consistency, asynchronous communication and circuit breakers, modern systems balances the trade-offs, often leaning towards AP, availability and partition tolerance for user experience, while ensuring CP for business critical operations. Hope this gives some clarity on which use case, which requirement need to be designed with what priority in CAP. Thank you.